where you are in terms of what you have to master and what you've already kind of started mastering, right? So let's go to teaching, right? I always mean to rename those, but teaching, intro, and exam 2 practice, right? So, it's a couple things. Again, the next actual exam, which is not for a few weeks, that will again be 105 points maximum on the exam out of 100. So again, that 5-point curve kind of already built in, or 5-point bonus already built in. Right? I've stuffed the example, right? So anyway, couple other things. This one was not really useful, but like here's what I was talking about. Question from a prior exam. Suppose we had a file called temperature.csv, which contains the daily high and low temperatures recorded in Philadelphia. This came from the 2019 exam, by the way. The file is composed of 3 fields per line containing the date, the high temperature, and the low temperature. Each field is separated by commas. For example, the contents of the file might look like this, right? This isn't, and that's the point. When I give you like a file on paper, I'm not like asking it to be hard-coded or anything. I'm just saying, hey, the file you're reading is going to look like this, because it's not. I don't want it to be solved for any particular number. I want it to be able to work on any file that I give that's called this. So like here's the day, here's the next day, and that's the high and lows. High and low, and then ... to indicate that's going on. Write a program that calculates or prints the following: the day with the hottest high, the day with the coldest low, and the average temperature of the high temperature of the entire file. So we're kind of already learning how to do that with the Hurricane Tracker lab, where we're telling it to go to. We're also going to be learning to do a bit of data analysis today with today's lab. Today's lab is very directly applicable, not just to the upcoming exam, but also to your homework, right? Because we're going to be doing a lot of string split operations here. Another similar problem where here's a bunch of numbers, add up all the even numbers in the file, right? Then there's going to be a lot of functions like this where I'm giving you a function and a task. Like this one says, if it starts with un, remove the un. So untied becomes tied, unable becomes able. Necessary though, if it doesn't start with un, you add un in front of it. So necessary becomes unnecessary. And then a couple of things like this, like given a string, return true if the word contains cat in it, but the middle A can be any character. So kitty is false because there's no cat in it. Tomcat is in it, and catnip, right? That's got cat with a 4 instead of an A, right? So it's a wild cat because the middle character is a wild card. So a lot of problems like that. The only problems that we haven't gotten yet are the Monte Carlo, and which may not be on the second exam, depending on how I adjust stuff, and problems that require dictionaries, which I'll start teaching on Thursday. And dictionaries are essentially really powerful tools for solving problems like this. Given a string, write a function which returns the most common letter in the string, right? Use a dictionary to do this. And dictionaries are just really powerful. Problems like this one, where I talk about a coin game and stuff like that, and what your ratio of winning is, right? Write a program to calculate that. A lot of these problems are actually like statistically nasty to figure out, and the entire point of doing Monte Carlo, of what I'll teach next, is a big part of my philosophy is I want you students to be able to, if this is your only programming class, I want you to have tools to be able to say, well, I know how to do that. I don't know quite how to do this, but I know a way that gets me close to the answer, that so close that the answer doesn't matter. And Monte Carlo is that. It's basically saying, I don't know how a game of chance works. I don't know how to do necessarily the probability and statistical math, but I don't need to because I'm just going to play the game a lot and then count how many times I win versus how many times I lose, right? The question I've asked on an exam in the past, and now is an extra credit problem, is here's some of the rules for Monopoly. What are the chances that you roll two dice, they come up the same number, and you do that 3 times in a row. So you roll a pair of 3s or a pair of 1s, and then you do it again, and maybe you get a pair of 5s, and then you do it a third time and get a pair of 6s. What are the chances of that, right? And so calculating those kind of odds. But this is not a math class. This is a class where I'm teaching you how to avoid doing that math, because the math that I really like to do, and the computer's good at doing, is let's add 1 to the number of results. Let's add another 1 to that, and let's add another 1 to that. And then we'll divide by the total number of throws we made. So that's Monte Carlo in a nutshell, and we'll be going over that with a lot of games of chances that are actually scams. A lot of fun there. Okay. So again, that exam isn't going to be for a while. Week 11 is currently week 8. So, and I will be deciding where we go with that. So today's lecture will be primarily done in Runestone. We're still on file reading, still working on that kind of stuff. I'm going to go to Canvas to get to Runestone, just simply because it has a direct link, but I'll show you where it is on Runestone regardless if you just want to head directly there to the textbook. And like I said, today is directly applicable to, or we'll learn techniques that are directly applicable to Lab 7. Okay, if we go here to modules and scroll down to module 8, which is dictionaries, we will click on Thursday, and I've changed the link so that it should go to where we need it to go. And it's the project Exploring Common Words and SETI. And if you go instead to your main page over here, log in, right? Go to the textbook over here, Foundations of Python Programming. Scroll down, all the way down. It's over here on Project 11. Okay. So we're working on Project 11 in the textbook, and there's a direct link from Canvas. And today what we're learning about is something called Zipf's law. I know that's weird, such a weird word, I have to zoom into it and highlight it. Zipf's law. Aren't names incredible? Names are just incredible. So anyway, let's talk about this. All right. A lot of data analysis projects require a huge list of words. This was actually a very prescient sentence when it was written, and it's gotten more prescient as generative AI has been used more and more. I want to be very clear. I love AI. I know a lot of your English professors really don't like it because, ignore any philosophical implications about it for a second and the issues of copyright law. It's less the issues of AI in general for generating art and for generating text. The ethical issues around that is primarily that a lot of companies built their models using data that they pirated, essentially. And it's not only is that not cool that they did it without permission, and very much a rules for thee but not for me kind of attitude. That's actually pretty much the ethical thing, issue of the ethics right there, with the generative models being scraped from pirated data. There is, some companies do have an out that they argue in court, or they think they have an out arguing in court. For instance, when I uploaded my videos to YouTube, there's this big contract that they have me read, or I'm supposed to read, that basically, when I read it, I'm like, you get to upload your thing here for free and we'll keep it online, and in return for uploading it and keeping it free for people to see, we get to do whatever the heck we want with it. Whatever the heck we can currently think of with it. And when I'm reading this, I'm like, whatever they can think of, right, okay. So, and the question is, did they think of, when they thought of things, did generative AI fall under the terms of what they thought of? Now with YouTube, there are a number of things that, that they've used for that kind of stuff. And we didn't really have a problem with it because we called it machine learning back then. But again, there's a lot of branding issues. But one of the things that we love to see, and that uses a lot of AI stuff, is the automatic subtitles feature on YouTube. We love that. A ton of people love that. Not only just being able to automatically translate, automatically get words, and occasionally they're wrong, but being able to translate it as well on the fly. These are great features that are built in. On the flip side, being able to generate more and more YouTube poops is not really that great. More slop is just not great. And that's a huge issue. Anyway, I've kind of gone off track. The point being is that generative AI text is essentially really fancy, really complex autocomplete. It does not, when we're talking about text, it does not do the kind of reasoning that we really think about it. It's really just simply extremely fancy autocomplete, which requires knowing about probabilities and words, and it's this entire kind of thing that gets built and trained over time. It's a whole thing. But so, long story short, knowing how language works, knowing how words work is kind of important. And so what we're going to be working off today is a large list of words. We're going to specifically work on the list of 5,000 most common words. Now, another complete tangent. I love, there are various kind of restrictions you can put on trying to generate works of art and stuff like that. One of my personal favorites is Upgoer 5, which is a text, and this inspired a book. It's a comic. U.S. space team's Upgoer 5, the only flying space car that's taken anyone to another world, explained using only the 1,000 words people use the most often. So in other words, it's using only the only words he was allowed to use were from the list of the 1,000 most common words in the English language. Hence why it was called not Saturn 5, but Upgoer 5. Yeah. So, thing to help people escape really fast if there's a problem and everything's on fire, so they decide not to go to space. The thing to control which direction the escaping people go. And of course, my personal favorite, more funny voice AF for filling up space. This end should point towards the ground if you want to go to space. If it starts pointing towards space, you are having a bad problem and will not go to space today. So, lots of different. So this was only using the 1,000 most common words, and the author Randall Munroe did an entire book with explaining science concepts with the most common words. With the 1,000 most common words. Here we're dealing with a file that's already preloaded into Runestone, so you don't have to do anything with it. You just have to open it. You don't have to place it anywhere. But as we can see here, we have a list of words starting with the, be, and, of, in, to, have. And what it is that it's a file that has the rank, so this is the most common at rank 1, word, part of speech, so what the word is, and then the part of speech. This is the article, how many times they counted it in their data set, and the dispersion, which I'll get into. Okay. So this comes from the Word Frequency Data Project. It is a subset of their entire data. What does the common words in the search for and SETI have with each other? SETI is what's called the Search for Extraterrestrial Intelligence. It is a bunch of space satellites that are pointed, a bunch of satellites that are just pointed at space. And they're essentially just listening. They're listening for a signal of some kind. And we get lots of signals. Just most of them are just noise and background rate and background kind of thing. So how do we know what we're getting is a signal, a language, some kind of data that actually is there to be processed as to just random gibberish that we think is data? And the answer is that language, every form of communication follows some level of rules, okay? And that rule is Zipf's law. Sorry, one of those rules is Zipf's law. A simple way to describe it is that words in a language are not evenly distributed across the language. For instance, the words you might find in the language might occur more often than one word or another word. For instance, take the word the that I am emphasizing in the sentences I speak. Those words occur much more often than other words. Okay? So there's a straight, nice plot on a log-log scale that links very common and very rare words. If we have time, I'll show you that plot. So, and basically what Zipf's law says is that the most common word, in terms of commonality, each word in that ranking will basically will occur nearly twice as often as like the next batch of words. So for instance, the occurs twice as often as be and all the other words in kind of the same frequency of there. And then those words occur almost, but not quite twice as often as these words. And then we start seeing like these big jumps, these either two thirdenings or halvenings, right, between words. And so that's what we're going to be looking at today. So we're going to be asking some questions. What are the top 10 most commonly used words? How often does the frequency of the usage compare to the frequency of the least? What percentage of those top 25 most common words represent? And things like that. So as I've mentioned, we've got the word, the rank, and the part of speech and the frequency and the dispersion. Okay, dispersion is an interesting one, and that basically says how evenly distributed is this across all of our data. So that was calculated because there's a couple words that are occur in some places but not in others. For instance, they use the term re, and that has a very low dispersion of 0.47 because it is primarily used in legal writing, but you don't see it in general talking. Another word that I personally like that Terry Pratchett pointed out in his writing is fracas or fracas. Noisy, disorderly fight or quarrel. You pretty much only find that in newspapers. That word only really ever gets used in newspapers. Okay, that would have a fairly low dispersion. It does not get used in it doesn't get used in novels, it doesn't get used in general text, but it gets used in a lot of newspaper articles. And in this class, I guess, when I'm talking about it. So, all right, so we have this data. So let's talk about our first task. Our first task is very straightforward. What we're going to do, or relatively straightforward, in order to work with data, okay, and this is like the first step of being doing any kind of data science, and what makes data science this whole thing. Before we can analyze the data, we have to, get the data and put it into an organizable format. So we've done the getting the data part, or we've got it for free. It's in a file called words5000.csv. Let's go ahead and just simply confirm that it works, right? We're going to just simply do open, and then I'm going to type words5000.csv, CSV. The number of times I've typed something else like CVS is kind of funny. And so I run it, and I don't get any errors. But if I did 5001, I would get an error because it would say that file doesn't exist, right? So even though so that's the part of the reason I also love the textbook, because it allows you to do stuff and say, hey, yeah, we've just got this file just built in here into the web page. And you can pretend it's on the computer and just do that. So we have the file, see? You should just be able to do that and run it and boom, right? If you want to confirm it, right, printing the So let's first off and just simply say file is equal to this, and then we're going to print the file. Just to kind of see what we have. And as a reminder, when we do print on a file object, we're not really getting anything too interesting. What we see is that we've got an open file function, we've got the name of the file, and mode R, meaning that we are in the read mode. Makes sense. We want to read it. Okay? Now to iterate through it, we need to do a couple of, remember, there were 3 ways we learned to read a file. Way number 1, which we rarely will use. We're only really going to use this much, much later in the semester. And we use this basically when we only really use this for regular expressions, okay? When basically we're doing a kind of operation on the entire text file all at once. And that's file.read. That will take the file and basically store it in just kind of one big string. The other one, which is what I use extremely often because it gives me a lot of control, and that's what we're going to do today, is we are going to do lines is equal to file.read lines, right? And that's how I read a file. Okay? And to confirm, I'm just going to print lines. And I'm going to do this slice operation here. This is index 0 through 10. This file ostensibly should have has like 5,000 words in it, thus 5,000 lines. I don't need to print out all 5,000 lines. So I'm saying, hey, rather than printing out everything, that would print out everything, I'm going to do this. Print out the lines from index 0 up to, but not including index 10. And there we go. Boom. So there's our first line. Let's go ahead and throw it into a for loop instead. For line in the first 10 lines, print out the line. That way it's easier to read. Right? We're only working out the first 10 right now because it makes it easier to read. So, and then we've got rank, word, power of speech, frequency, distribution, and then we've got the first 9 words, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we have the first 9 words and not the first 10 because index 0, as everybody can see, is a legend, right? Makes sense? Just like how you'll have in your homework, you've got this legend. So we're going to just discard this and I'm going to work on the first 10 lines again. When we're done, when we go to solve the whole problem, I'm going to just simply remove this last argument to do the whole file, but this now will go through lines 1 through 10. And we can just simply say 98, 97, 99, 97, 96 is the last one, 98, 97, 99, 97, and then 96 is the last one. So there we go. So we are reading this file and we're printing out this stuff successfully. So this is step 1, which is that we can confirm that we're reading the file. The next step is to take this file and store it into 5 lists, each one for holding the date for each part of the data. Okay? Right, we have 5 fields, so we're going to store each of those. So what we're going to do is we're going to create 5 lists. It's going to be very repetitive right now. Okay, so we have 5 things. We have, and conveniently we can do them all as like this rank is equal to an empty list. This word, the next field is the word, right? So we have the rank, number 1, number 2, number 3. The word. Then we have this letter here, A, V, C, I. They've got a legend over here. A, V, C for conjunction, I for preposition, T for the infinitive to, as opposed to, like to be, to run, to go, to laugh, to sing, to cry, right? As opposed to the other, the non-infinitive to, like I went to the supermarket. Okay, the T. t infinitive 2. So anyway, this is, that single letter refers to the part of speech. So I'm just simply going to, so we've got rank, word, part for part of speech. And then finally, we've got the other two. We've got the frequency of the word. Freq is equal to this. And then dispersion. So all 5 of those create 5 separate lists for each one for each of those fields. Make sense? So now what we need to do is populate those. Now, for your homework, the Lab 7, you don't need to create separate lists for each of them because you're just simply, because for your homework with the Hurricane, you're just simply saying, okay, move the turtle here, then here, then here. We don't need to save our answers for later. Here, though, as we're going through it, we do want to save our answers. So rank, word, part, frequency, dispersion. Okay. So now what we're going to do is, as we read our lines, we should take our line and we need to separate those. We got to get our data into a usable format. Now, the thing about CSV files is that we almost always will know how to get them into a usable format. Each line is a nice big string, but the string is separated by commas, hence the name CSV, comma-separated values. So take a look at, so right now I'll just print out line, and I'll print out also line dot split on comma. And was never closed, right? Run. We're printing out an extra new line here, so what I'm going to do is I'm just going to add in a strip over here to clean the line up. And we'll see that what we've got is here's the original, and then here's the what happens after we run split on it. Make sense? Right, everybody? So original, and then split turns it into 5 separate fields. 1, 2, 3, 4, 5. The things separated by each of the 4 commas. Make sense? Right? I would say probably this part that I'm doing right now is probably the most important part of the lecture because it's the part that's directly applicable to your exams and to your Lab 7. So 1, 2, 3, 4, 5. We've got those things. So let's go ahead and, so now that we've got this, what I'm going to do is instead I'm going to just rewrite this a bit. Still do this kind of the same thing. I'm going to say parts is equal to line.split. It will take that line, split it into parts. Then I'll just simply print out the parts to basically show I've got nothing up my sleeves here, right? It's the same deal. I've just stored that. Rather than printing this directly, I've put it in a variable, then I printed it. So, but now each of these is like a digestible format. For instance, I could do part 3, 0, 1, 2, 3, and now I'm going to get the number for each of those. Make sense? So what we're going to do is we're going to take each part of this and add it to the list, the appropriate list. For instance, ranks dot append, not ranks, but rank dot append parts 0. And then I'll print out rank to show you what that does. But append just simply adds things to a list. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Specifically, we've got the string, right? String 1, string 2, string 3, string 4. Let's go ahead and turn those numbers into actual numbers, shall we? Int. Rank.append. And now we've got the number as opposed to the string, right? Now I'm going to be a bit lazy. We know we need to do this for the same operation 5 times again, so I'm going to make use of copy paste. So, keyboard, up, 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 hit, press and hold shift, up, 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 hit control or command as the case may be, hit left, 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 control C or command C on a Mac, down, 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 paste, tab, 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 copy. Paste, paste, because I know I need to do the same operation for each of them. Paste, and now we go through this one at a time. So the order is rank, sorry, 1 second, I'll show you again. Just double checking. The order is rank, word, part of speech, frequency, dispersion, rank, word, part of speech, frequency, distribution. And now we just need to make sure that each part is correctly converted. The word is a string, so we definitely don't want to turn that into an integer because that will make the computer very unhappy. Watch as the computer gets very unhappy. Right? Can't turn the into an integer. So we remove the int from here because we can't convert it into an integer. Similarly, the part of speech, that's a letter. It's a string. So we're going to keep it that way. The frequency is a number. It's a whole number. So we're going to turn that into an integer. And then finally, the dispersion, that's a floating point. So rather than being an int, that's going to be a floating point now. Make sense? So let's go ahead and show you that I've got all this, by the way. Now that I've kind of put them all into the list, I'm going to show you a neat trick that is completely unnecessary for the exam, for everything in general, but it's a really neat trick built into Python, right? So just watch me for a second, and you should be able to see, for RWPFD, why those letters? It's the first letter of each of these. That's the only reason I choose them. Typically doing that is like bad practice, but you'll see in a second. Comma, what? You can do that? Yes, you can. In. Zip. What? Zip. Yep, there's another function besides range. This will literally not be tested on the exam, so if you're panicking now, don't worry about it. You can forget about it in 3 minutes. Okay? I just want to show you in case it comes up. Rank, comma, word, comma, part, comma, frequency, comma, dispersion. What this allows you to do is iterate over multiple, zip allows you to iterate over multiple lists at the same time, which can be very useful, assuming they're all the same size, which they will be. So print copy. Probably would have been able to type that quicker than I had just copied it. And now, as you can see, I printed out each of those. The only print is in here, and that prints out basically all the stuff that we've added to the list. We've confirmed that we've added them to the list. Zip is kind of useful. It is one of two kind of really useful tools that we have for iterating over stuff in Python. The other one is another term that we do for index item in enumerate, and notice I'm doing this completely commented out, and then my list, and that allows you to go iterate over the index and the item at the same time. So some really, I wouldn't say they're advanced Python tips, but definitely not beginner in the sense that I'd expect you to know them for exams and stuff like that. They're just really neat tools, okay? But we've got our part here, right? Split the line into 5 parts and put each of those in the appropriate list. Now let's just simply do that by removing that 11 to now work on all lines. Okay. Now, I'll go ahead and share this Time for more language jokes. Another XKCD comic. Language also isn't constant over time. The frequency of a word today will be frequency of the word later, later as well. For instance, frequency of the word of the word sustainable in U.S. English text as a percentage of all words by years. Right? So here is the x-axis, the year. It projects out to 2140. And then what we have here is what on the y-axis we have something that's important to this lecture called a log scale. So notice that over here we have 0.1%, 1%, 10%, 100%, 1,000%. Each of those, each tick mark, right? This isn't 1, 2, 3, 4. These aren't equally spaced. Each tick mark is 10 times the previous mark. That's what we call a log scale because it uses a logarithm. A brief note on logarithms. Most of you are probably scared of like an operation like where if I do something like this, where if I ask you to compute, yeah, we're doing a lot of asides today, but there's just too much useful information for you to get today. Just too much, okay? Most of you are probably terrified by logarithms or bang your head against them and think they're stupid, which, to be fair, a lot of you have been taught them in a very stupid way. For instance, trying to know, just kind of being able to go, okay, what is log base 2 of 16, right? And you got it, and you're basically reverse solving it through the property of the fact that, you know, that we know that this is, let's see, 2 is, it's 4, right? And we know this because 2 to the 4th is equal to 16, and basically that's what the property is, right? 2, 4, 8, 16. We know that, or to generalize it out, we know that log base of A is equal to C is A to the, B to the Cth power is equal to A or some, no. This is utterly useless for all of you, right? This makes no sense whatsoever. It is not a normal way for humans to think, right? This is both truthful but unhelpful. So let's actually go over for like 2 minutes, what does this question actually do in a useful format? Log base 2 of a number asks, how many times can I split this number in half? That's all it asks. How many times can I split this number in half? Let's go ahead and just focus on easy examples for a second. Same thing, log base 2 of 16 is asking, how many times can I split 16 in half? Let's draw it out, because nothing makes me feel better than cheating at math by just drawing something. We can split 16s in half into 8s. We can split those 8s in halves into 4. We can take 4s and we can split those 4s into 2s. We can split those 2s into 1s, and once we get to 1s, we can't really do anything else, right? That gives us a grand total of 1, 2, 3, 4 splits, right? There's 4 layers to this. So log base 2 of 16 is 4. Does that make sense to everybody? We can, that is what all logarithm is. A lot more useful, right? I don't know how many of you were actually taught that in math class. Yes, no? No? Maybe a couple nods, but that's what a logarithm is. Now, in case you're just wondering, log base 10 of some number, like 10,000, is asking how many times can I split this into tenths, right? We can split the 1,000 into tenths of 1,000. So 10,000 to thousands, then those thousands into hundreds, those hundreds into tens, those tens into ones. We can't go any further, so log base 10 of 10,000 is 4. right? And you can double check your math to make sure you're correct. Now, of course, this is like, well, what about like something like, 14,000? Well, it's probably a little bit above log base 10 of 10,000, right? But simply put, we're not using this technique to solve what a logarithm is. We're using this technique to understand what a logarithm is asking, which is how many times something can be broken apart. Okay. Anyway, going back to the comic. So, frequency of the word sustainable in the U.S. English text as percentage of all words by year. In the 1960s, the word sustainable, tenth of percent, 100,000, 10,000, hundreds of thousands, fairly not used. Whereas, like, close to the present day, we can track it over time and draw a line through it. In present day, it's somewhere between, the word sustainable occurs in somewhere between thousands and hundreds of thousands of percent of the time. However, you can always extrapolate data. And then if we keep going based off of this line that we've created, by the year 2040, year 2036, sustainable will occur on average once per page. By 2061, sustainable will occur once on average per sentence. And then by the year 2109, all sentences will just simply be the word sustainable repeated again, again, and again, and again. Hence the punchline, the word sustainable is unsustainable. All right, so let's get back to programming. So now let's go ahead and understand what I mean about what I'm talking about with Zipf's law. Let's look at the overall usage of the 10 most common English words. So first thing we want to do is turn the frequency count for each word into a percentage. Okay? Calculate the total usage percentage of the top 10 words in the list. Store this result in top 10. Then at the same time calculate the percentage for bottom 10 words in the list and store that result in bottom 10. So first thing we're going to do is we are going to just simply go over here and copy paste our code. Right, I've already shared it with you. You can reload. But I'm just copying and pasting all this code so I can paste it into here. So I can go through the word. So I can go through this. I'll delete the commented outlines that I don't need. I have your code here, words.csv. Got my rank. I've got my rank list, my word list, my part of speech, my dispersion. I read the line, I split it up, I add everything, and now what it's asking is, what is the percentage does the top 10 words represent? Just simply briefly, it's basically asking, hey, these first 10 words, which are word.1 through 10. You don't have to copy this part down, 0. First 10 words. Right, because we didn't include the legend here. First 10 words. The, be, and, of, in, to, have, to, it. Right? I want to know what they occur. We have a frequency count for each of them. Right? Here's the first 10 words. Okay? Like, for instance, the was counted in our word count. The occurred about 22 million times, be occurred 12 million times, and so on and so forth. All the words we counted can be calculated like the total number of words counted can be calculated very easily by just saying, hey, that word frequency list, what's the total of that? Run, and that is 329 million. And so it's asking us, hey, these top 10 words, what percentage is that? What percentage does that represent? It's actually pretty much given you everything you need to solve the problem, right? You're looking for a percentage. So it would just be, yeah, with the way time is going, I'll just do this one. We've got the word, the frequency. So the top 10 words are these things. So the percentage would be frequency of the top 10. We're going to go ahead and add all those up. I'm going to be lazy. Once you know Python, it really lets you be lazy like this. See? So those first 10 words have a combined total of 91 million occurrences. We're going to go ahead and divide that by the number of times all the words appeared. And that gives us an answer of 27%. Let's go ahead and just simply test. Sum frequency of the first 10 divided by the total amount. And it wanted us to store this in a variable, top 10. And we see, yes, that is in fact the answer. So think about that for a second. The, and, of, be, to, these words account for 27% of the English language. 27% of the English language. And this is true for all languages, although not those specific words. For instance, not every word has the same language. For instance, in the language Hebrew, you've got et, which is the direct object marker. It threw me for the longest time when I was learning Hebrew because I didn't understand the idea of a marker, right, which is not a word that means anything, like wa in Japanese or o in Japanese. Et is, in Hebrew, is kind of the same thing as o in Japanese for marking, basically, is this thing the direct object of a sentence? Some languages basically highlight that for you, which is nifty. And the weirdest thing is that as you're learning it, those things become invisible, like you don't actually hear them or consciously add them to a language. It's interesting. So those language, that makes up a lot. Now, it's also asking for the bottom 10, right? The percentage for the bottom 10. And this is very much a copy-paste kind of deal. Copy, paste. For the bottom 10, all we have to do is then, rather than doing the first 10, right, this was from index 0 up to, but not including index 10, if we know how to use our so by knowing how to use sum, we really kind of didn't have to do a running sum, which was nice, but if we know how to do slices, we can do this. Negative 10 up to the end. Negative 10, right, negative index negative 1, remember, is the last item in the list. Negative 2, second to last item in the list. So on and so forth, right? So let's go ahead and just simply grab this. Print, just kind of just show what these words are. Print, word. These are the last 10 words. So word 4991, 4992, 4993, up through word 5000, which are words like censor, laundry, manual, pistol, naval, plaintiff. Right? You can imagine with all the legal writing there is, the word plaintiff occurs a lot, but at the same time, not too much. And we actually see that it occurs, according to this, these these words, even though they're in the top 5,000 words of English, right? They occur combined less than a single one of these. It occurs, this is normal percentage, 27%. So 100, so 10th of percent, 100th, so 1.5 hundredths of a percent. So very unoften. And again, this is true for every language, not necessarily those specific words, just this breakdown of words that are frequent are really frequent, and words that are not frequent are really not that frequent. Okay? So what we're going to do is I'm going to show you some really cool stuff in in a library called Altair, and I'm going to just need to log out of this class for a second so that I can go back to the last semester. I do this every semester, so I can grab the code I grabbed from previous semesters that I wrote, because I don't want to write this from scratch, because the library I don't use this library for graphing. Python has some great libraries. Altair is great because it is built into the web browser. It can do this. But the primary graph library that I use for my PhD and other stuff is matplotlib. Amazing library for making graphs in Python just by throwing numbers at it. So if you want to do data in Python, you want to learn matplotlib. But the idea here is that this kind of thing is a bit hard to understand because we're looking at numbers, so we're going to look at lines representing numbers instead. Okay? We're going to use Altair to graph the frequency of words on a y-axis against their rank. And log graphs are hard to understand, right? We've got things like the Richter scale for earthquakes, where a magnitude 6 and 7, this is a log scale again. So a magnitude 7 earthquake is not just a small increase. A magnitude 7 is 10 times as strong as a magnitude 6. It's a very huge difference, okay? This is log scale, which it makes it easy to say, and it avoids this kind of issue. Fuel energy density in megajoules per kilogram, sugar, coal, fat, gasoline, uranium. Science tip, log scales are for quitters who can't find enough paper to make the point properly. All right. What physicists and other scientists, any scientists, will get excited about is when data like the data we're working with can be graphed into a straight line in some way. And that's what we're going to see, okay? So what I'm going to do is I'm going to go and, boop, 1 second. Yeah, I zoom in for a lot of stuff. So change course to, change course, come on. You can load. You can do it, Runestone. I believe in you. I believe in you, Runestone. Right. And now we'll go back to spring 2025, Rosen. Obviously, you can't do that because I'm rolled. I'm going to go ahead and scroll up to the same problem, and I'm just going to grab my code from last semester, which will look very similar to the code for this, to what we've done so far this semester. Copy it, and now I'm going to go and do the exact same thing, which is change course, go into fall, and now I'm just going to go back to the exercise we were doing and paste in the code so we can take a look at it. Okay. Why didn't I do that before the lecture? Because I'm lazy. Okay. Okay. A couple things first. I'm going to definitely share this code with you. Okay. And now I've pasted this code, which I will share with you. Save and run just simply to save it in. And what we're going to do over here is we are going to, you'll notice I have things commented out. I'm going to comment those back in, and what I'm going to do is I'm going to comment out the lines that have logs in them, that log operation. So let's go ahead and just see what I've added. Import Altair. Altair is a graphing library. There's an exercise, a couple exercises in projects. It's not in the textbook proper. It's in the appendice with a bunch of the other projects, and you learn it as part of doing some of the other projects. If you want to learn more about it, you can, but I'm not going to test you on it. It's mainly I'm just kind of it's what I got to do to show you, and it's you'll see. It's easy enough to read.
What chapter is it?
It's not in the chapter. It's in the appendix. It's like if you like over here. It's in Kiva. So like when we did the Kiva stuff, there was a project on using Turtle to graph it, and then
Yeah, I only see my own code.
Altair.
It doesn't work.
So okay. So what we've got over here is, let's see. So let's see. I called this data instead of file. So let's go ahead and Just change that to file. And then let's go ahead and grab this instead. Let's go ahead and edit this a bit. Lines is equal to B. I'm just making this match what I have this semester. Lines is equal to file.readLines. And then I can just do this. Lines is equal to lines, everything but the first one, right? And then for line in lines, okay? Run it to confirm that it still works. Math is found but unused. Yep, that's correct. Okay, so now what do we have here? For every line, we split the line up just like we were doing. And what I did is that I've got the exact same code that I had above, right? Where I'm making the rank, importing the rank, word, part of speech, the frequency. All those things got added. The only thing that's been added right now is lines 17 and 21, which are commented out, so we can ignore those for now. Okay, that's just simply I just simply have those as on-off switches for doing some processing. So now that I've split it up, it's actually ridiculously simple to throw into Altair, the graphing library, which has been imported. And let's just read what it does. It's 5 lines total. It's not always that easy. The bottom one's probably the easiest one, and we'll get to it last. But that just actually simply says, show me the graph. Right? That's kind of obvious from enc.display. But so let's stop at the top. Data is equal to altair.data. Okay, that makes sense. Why I'm naming it data. Altair, so the package altair.data. So this creates data from whatever I give it. Ranking creates a data. It creates one pair of data called ranking, which it gets from rank, and then a data called frequency, which it makes from our freq list. So it just turns it into its internal format. Basically, we're telling it what the data is. I tell it, hey, I'd like you to make a chart with this data, and we're going to take that chart and we're going to store it in chart. Next, I want to say, hey, can you make the markings we're going to use on the graph to indicate how the graph is made is going to be chart.markLine. In other words, make me a line graph, okay? And then finally, that line graph, let's go ahead and make it, let's actually make the line on a graph by encoding it. And I say, hey, the X is going to be the ranking and the Y is going to be the frequency. Make sense? So basically it says, hey, this is the data. I want you to make a chart with it. Again, I'm going to share all this code with you. Okay? In fact, I can share it right now. Okay? And so if I run this code, it's going to give me a warning here that I've imported math but not used it because the stuff I do use it for has been commented out. And we see this really unhelpful chart right here. It's very not great. Okay. Export as SVG? No. Export as PNG. So we're going to just kind of look at this graph and zoom in. Frequency, 20 million. Makes sense, right? The occurred 22 million times or something like that. And we can see that all the way at close to rank 1, right? We had the, and then not too far off, it drops off like crazy, right? It's just like a vertical line with a bit of jittery over here, right? And that jittery is just probably a bit of mess. So what we're going to do is we are going to start by swapping out our frequency. Base 2. Here. So math integer 9.3. Okay. So first, let's talk about the math function. Sorry, the math library. Okay. Almost every single programming language has a math library, and they all work very similarly. Import math, And they do things like have all those annoying math functions you love / hate. Okay, for instance, math dot sine of 3.14159 gives you something pretty close to 0. Whereas if it's the cosine, it will give you something pretty close to 1. All right? Or -1, rather. So we've got, basically we've got your trigonomic functions built in, but the one we care about is, the two reasons you're going to probably import math is math.squirt. Well, not squirt, it's short for square root, SQRT. So, for instance, the square root of 84 will be a bit more than 9, makes sense. And then math.log, right? And if I pass in a number by default, like 100, it's going to give me, interesting, it gives you log base. It gives you math.log. So it gives me 4.6. If I do math.log, and you don't need to memorize what this is, but like if you could do like 2.71, you'll get something that's close to 1, because by default, if you don't give it a base, it's going to assume the base is the number e, which is 2.7, which has all these special properties, 2.71 and a bit. It's one of those very important numbers, like pi is very important. Okay? Very, very important number. Okay. Not my job to explain why it's important, so I won't. Okay. So, if you want it to be useful, though, what we can do is we can, or more useful to you, and put it into a format we can understand. We'll say, give it a number, like let's do 128, and then 2. Why 2? What's the 2? 2 is the base. So now we can go back to asking this question, which is how many times can I split 128 in half? And the answer is 7. Math.log 256, big numbers in computer science, it's 8. Right? So how many times can I split that in half? So that's what you're going to see here. So now what we're going to see here in this code is we see what happens if I do frequency.append math. And it says math.log, and then I don't know why I have a 2 here. I'm going to put a 10 here, but I'll remember. Frequency, we're going to change the frequency so that we're not looking at the frequency of, we're not going to look at 2 million. This is no longer going to see 20,000 or 20 million or 15 million or 10 million. It's going to show a much smaller number. But if I run it, interesting. Oh, because I did not comment out the other bit. That's why. That's important. So now we'll see, suddenly the graph has got a bit simpler. We see 0 through 8. Now, again, going back to the example of like the Richter scale, right? Each of the frequencies here is 10 times, going up 1 on the scale means it occurs 10 times as often. Make sense? So over here, right, is our 22 million. Well, a million is 10 to the 6th. So this is slightly, 10 million is 10 to the 7th, so this is slightly above 10 to the 7th, so it makes sense it occurs right over here. And so we still have this shut off, but we see, okay, the frequency counts are kind of going down, but not as fast. Log base 2, right, if I did this as log base 2, the numbers will change. 25, 20. And now the y-axis is basically saying this is 2 to the power of 20, 2 to the power of 25, so on and so forth. Let's keep it back at 10. Now, of course, or not of course, let's go ahead and see what happens if we change the rank to follow the same idea. So we're going to take the log of the rank as well, the base 10 log. So that number on the bottom is going to be, we're going to ask how many times can be this number be split into tenths. And when we do that, we see actually we get this kind of straight line, showing that these first numbers, right, these numbers, these first 100 numbers, say these first 10 numbers, occur a whole lot. This is numbers, these are the first 10 numbers over here. These occur millions upon millions of times, tens of millions of times. Whereas the next 100 numbers, they each kind of occur millions of times to maybe hundreds of thousands. And then the next 1,000 numbers occur tens of thousands of times, hundreds of thousands and tens of thousands of times, right? So, and then finally we get to the next, the rest, which is like numbers 5,000, number, the ranks 1,000 to 5,000. And we see that these occur I think it's tens of thousands to thousands. Yeah, tens of thousands to thousands of times, so a whole lot less. So that's what this log scale is telling us. And it's a bit hard to interpret log scales because we're not used to thinking. Humans are terrible at big numbers. We just are. It's just not it's not just something our body really needs to understand to survive. Like, it's just not something we're good at. It's hard for us to understand scale and magnitude. Okay? It's part of the reason why we find looking at big things like the Grand Canyon or the Empire State Building or the Burj Khalifa to be just so awesome, right? We look at it and like, whoa, that's big, because it's really hard for us to get this across. All right. But this is very interesting. And like I said, all languages kind of follow this function. Let's go ahead and look at Wikipedia before I dismiss the Zipf's law. Right? Inversely proportional to its rank. And we see here that we get a graph over here for the most common words. And so the word is thus the most frequent by word, it by itself accounting for nearly 7% of all word occurrences of and. And we see actually if we're analyzing like signals from animals, like the chattering of squirrels or humpback whale calls, that certain sequences and frequencies occur in a system that follows this kind of formula. It's kind of crazy. And the statisticians have all these, crazy math-related things for it. But honestly, it is just really cool occurrence. Yep. Well, recent analysis of whale vocalization samples show that they contain recurring phonemes whose distribution appears to closely obey Zipf's law. So, to wrap up, now that we've gone off the rails multiple times this lecture, what's important for you to understand and remember for your lab? Remembering how to read the file and how to split it up and then get those individual parts. For your lab, you'll have a turtle and you'll just want to tell t.go to and then tell it where to go to as part of the for loop. And then it'll move around. Now, the other big part is that when we're working on your lab, once again, when you open up the file, that file is not going to be on the same level, right? It's going to be in a folder next to irma.py, right? It's in a folder. And to open up the file in the folder, what we're going to need to do is just type data/words.t. Let's go ahead and see that in action just a little bit. Let's go to, I'll open up my text editor. Just a little bit. So this, right? You want to open it. Here's your data. Open data/irma.csv. And that's how we open it. And then your next step is to do what we were doing, which is lines is equal to data.readLines and the like. All right. So I'll make sure to upload this. And I think that's a great stopping point for the day. If you've got questions about the exam, I'll try to briefly answer them. Otherwise, I can try scheduling an individual Zoom call if you want me to go over your exam stuff privately, in case you're self-conscious about that.